Section 2. Subspaces, basis, and dimension. After completing this section, you will be able to answer the following questions. What is a subspace? What is a basis of a vector space? What is a dimension of a vector space? How are these concepts applied in real-world problems? A subspace is a subset of a vector space, that is, itself a vector space, following the same rules of vector addition and scalar multiplication. Subspaces allow us to focus on smaller parts of a vector space that are still mathematically robust, making them useful in simplifying problems and understanding the structure of data. Let's see how we can define subspace more formally. A subset W of a vector space V of a field F is called a subspace if it satisfies three conditions. The first condition is that the zero vector is in W. The zero vector is a vector in which all components are zero. This condition says that the zero vector must be in W. The second condition is closed under addition. It means that if vector u and v are in W, their sum u plus v must also be in W. The third is closed under scalar multiplication. It means that if v is in W and she is a scalar from F, she v must also in W. Let's consider R3, the vector space of all three-dimensional vectors with real components. A common example of a subspace in R3 is the subset of all vectors lying in a plane through the origin. For example, consider all vectors that lie on the xy plane. This set W is a subspace of R3 because the three conditions are met. First, the zero vector is in W. Second, it meets closed under addition. If u and v are in W, then u plus v is also in W. Third, it meets closed under scalar multiplication. If she is a scalar and v is in W, she v is also in W. Accordingly, the set W is a subspace of R3. Let's go on to another concept, basis of a vector space. A basis of a vector space V is a set of vectors in V that is both linearly independent and spans the entire space V. Let me clarify what linearly independent and span mean. What do we mean by linearly independent? A set of vectors is linearly independent if no vector in the set can be written as a linear combination of the others. In simpler terms, none of the vectors are redundant. Each adds a new direction to the space. Next, what does spanning mean? A set of vectors spans a vector space V if any vector in V can be expressed as a linear combination of these vectors. It is not easy to understand the concept of basis of a vector space just by its definition. Let me give you another explanation. A basis is a special set of vectors that serve as a starting point for expressing all points. For example, in a plane, a two-dimensional space, if one vector extends horizontally and the other extends vertically, then, using these two vectors, you can go to any point on the plane. In other words, A basis is a standard guidepost that allows you to move anywhere in space. Combining these vectors allows you to express all the vectors in that space. And there is a set of vectors that is not a basis. In order to be a basis, a set of vectors must be linearly independent and must span the space. Any set that does not satisfy these conditions cannot be a basis. Specifically, there are the following cases. First, a set of linearly dependent vectors. A set of linearly dependent vectors cannot be a basis. For example, in a two-dimensional space, if two vectors point in the same direction, they are linearly dependent and cannot represent all points in the plane. In such a case, the set cannot be a basis. Second, when there are too few vectors. A set of vectors is also not a basis if the number of vectors is less than the dimensions of the space. For example, in 3D space, two vectors alone cannot represent all the vectors in 3D space. Such a set is also not a basis. Third, when there are too many vectors. If there are more vectors than the dimension of the space, they will not form a basis either. For example, if there are three vectors in a 2D space, they will not form a basis because they are linearly dependent. In two-dimensional real vector space, the standard basis can be expressed in this way. These two vectors are linearly independent. Neither is a multiple of the other, and they span the entire two-dimensional space. Any vector in this two-dimensional space can be written as a linear combination of E1 and E2. Thus, a set of vectors E1, E2 is a basis for a two-dimensional real vector space. Geometrically, a basis provides a set of directions in the vector space. In a two-dimensional space, a basis consists of two linearly independent vectors that can be used to reach any point in the plane. In a three-dimensional space, a basis consists of three linearly independent vectors that can be used to reach any point in space. A basis gives us a coordinate system for describing any vector in the space using unique coordinates. A basis vector is one of the vectors that make up the basis set. It is a single vector from the group of vectors that span the space. If a vector space has dimension n, then the basis consists of n linearly independent basis vectors. A basis is a set of basis vectors. This is an example of basis vectors in R2. They are linearly independent and span R2. So, they can form a valid basis for the space. That is, any vector v in R2 can be written as a linear combination of v1 and v2. A standard basis vector is the set of basis vectors that are most commonly used to define the coordinate axis in a vector space. In n-dimensional Euclidean space, Rn, the standard basis vectors are aligned with the axis of the space, and each has a value of 1 in exactly one coordinate, with zeros elsewhere. In R2, two-dimensional space, the standard basis vectors are these two vectors. In R3, three-dimensional space, the standard basis vectors are these three vectors. These vectors are called standard because they are aligned with the coordinate axis and are commonly used as a default basis for vector spaces. Let's go on to another concept, dimension of a vector space. The dimension of a vector space is the number of vectors in any basis for the space. Intuitively, it tells us how many directions we can move within the space, or equivalently, the minimum number of vectors needed to span the space. Formally, dimension of a vector space can be defined in this way. For a vector space V, the dimension of V, denoted as dim_V, is the number of vectors in a basis of V. Simply put, the dimension of a vector space is the number of independent directions required to create all the vectors in that space. Let's consider by simple examples. One dimension is a world on a straight line. In this space, you can express all points by moving forward and backward. In other words, just one independent direction is sufficient. Moving only left or moving only right is sufficient. Two dimensions is a world on a flat surface like a paper. Here, you need two independent directions, left and right and up and down. This allows you to reach any point on the flat surface. Three dimensions is the world of a three-dimensional object. Here, three independent directions are needed to reach any point in this space: left and right, up and down, and front and back. In this way, the dimension refers to the number of minimum directions needed to get anywhere in that space. That is, the minimum number of vectors to span the space. The higher the dimension of a vector space, the more independent directions are needed. Let's see some examples of dimensions. First example. The vector space R2 has a standard basis of E1, E2. Since there are two vectors in this basis, the dimension of R2 is 2. Second example. The vector space R3 has a standard basis of E1, E2, E3. Since there are three vectors in this basis, the dimension of R3 is 3. Let's see an example of subspace. Consider the subspace of R3 consisting of all vectors lying on a line through the origin. It can be written in this way. In this case, the set 1, 0, 0 is a basis for W, and since there is only one vector in this basis, the dimension of this subspace is 1. Let's see another example of subspace. Consider the subspace of R3 consisting of all vectors lying on a line through the origin. It can be written in this way. In this case, the set 1, 2, 3 is a basis for W. Since there is only one vector in this basis, the dimension of this subspace is 1. The concepts of subspace, basis, and dimension are applied in data science for various purposes. The first is understanding data structure. Understanding dimension enables us to grasp the dimensionality of the space in which the data exists. It represents the complexity of the data. The second is simplifying complex problems. Subspace relates to breaking down a vector space into simpler parts. It makes analysis and computation easier. The third is dimensionality reduction. Subspace and dimension can be applied to dimensionality reduction, a method to find lower dimensional subspaces within data. Dimensionality reduction can simplify machine learning models, reduce calculation time, and mitigate overfitting. The fourth is feature selection. In data analytics, subspace and basis relate to feature selection. Selecting a basis for the feature space is equivalent to selecting the features with the highest information value, which helps build more effective models. In this section, we have explored concepts of subspace, basis, and dimension. A subspace is a subset of a vector space that is itself a vector space, following the same rules of vector addition and scalar multiplication. Subspaces enable us to focus on smaller parts of a vector space. A basis is a special set of vectors that serve as a starting point for expressing all points. Combining these vectors enables us to express all the vectors in that space. The dimension of a vector space is the number of independent directions required to create all the vectors in that space. In machine learning, these concepts are useful for various purposes, such as understanding data structure, simplifying complex problems, dimensionality reduction, and feature selection. Thank you for watching. Please thumbs up and subscribe to my channel.